All right, so again, we're supposed to find the critical number. So these are just kind of getting us practice into finding if it's a critical number or it's not a critical number. All right. Looking at this equation, where is f of x continuous or not continuous? Well, ln of x, what does ln of x look like? Well, ln of x is going to look like that, and x basically has to be greater than 0 because this is, again, ln of x. And so this is only going to work for greater than 0 values. And so what happens is when we take our derivative of f of x, well, we get what? We get 5 over x, and then we get minus 1. Okay. And now we could write that as a whole fraction as what? 5 minus x over x. And so however we want to do it, basically, the key thing is, x cannot equal the 0, and that's going to be one key thing. And also, that 5 is going to be a kind of a problem too, because it's going to be has to be greater than 0. So because of this part, the ln, so it's going to be greater than 0. But if we have 5, then that's going to give us a 0 there, and so we know it can't work there. So x basically is equal to 5. That's going to be something we have to look at to see if it works or not. All right, so what do we have? Well, we have our thing. Again, 0 is where we have to start at because we can't do that. So we know it's not going to be 0. So then we go up to 5. So that's going to be what we think is a critical number. So let's plug a number in between here. 5 minus 2 is 3 divided by 2, so that's going to be a positive number. What about something out here? Maybe, oh, I don't know, 10. That's a big number. 5 minus 10 is going to be a minus 5 divided by 10. So that's going to be a negative number out here. All right. So it looks like we're increasing and then all of a sudden we're decreasing. So it looks like, we're having pluses up to here and minuses over here. And what this ends up being is that's going to be our critical number, because all we have to have is we have to have it greater than 0. So 5 is going to work for this one. And we know that we're increasing here. So this is increase and this is decrease. And so we're going from 0 to 5 increasing. And from 5 to infinity, we're doing what? Well, let's make it better than that. And then we'll say decreasing. Okay. So again, this one we had to know, what did ln look like? Well, it looks something like that. And so we know we had to be greater than that 0. And so then that doesn't mean anything here. So then we have to look at our numerator. And so that was going to give us the 5. And so then that was where we looked from, 0 to 5 and then 5 and greater. And so then that was our critical number. All right, so let's look here. Some items to note. So we can't assume that all partition numbers for the derivative of f are critical numbers of the function. So to be a critical number of f, a partition number for f prime must also be in the domain. So if it's not in the domain, then it's not going to be there. So that's kind of the first key. And then the second, the intervals on which a function f is increasing or decreasing must always expressed in terms of open intervals that are subsets of the domain. So you notice we always put, parentheses. We didn't have no brackets were used or anything like that. It was always open intervals. Okay, so those are two things to note when you're writing things out like this. All right. So here, when the graph of a continuous function changes from rising to falling, a high point or local maximum occurs. And then when the graph changes from falling to rising, a low point or a local minimum is going to occur. Now, in this figure below, what we have is we have high points occurring at what? Well, they have at C3 and at C6 up here. And low points where at? Well, at C2 and at C4. Okay. And in general, we call f of c a local maximum if there exists an interval such from m to m to n, containing a c such that f of x is less than or equal to f of c for all x that's within that interval m to n. And also, we need to note that this inequality need hold only for numbers x near c. So just close to c, not all far distance away, just really close. And that's why we use the term local. It's not, going from this side clear over to this side. We're looking really local from like here to here, really close together. Okay. So the y coordinate of the high point C3, f of C3 is in the figure below is a local maximum. And again, that's this point right here as the y coordinate of C6 and f of C6, which is over here. Okay, so those are, again, they're looking just right really close around here and right really close around here. So those are, the local areas that we're looking at. And same thing would happen if we're looking at the local minimums. We're looking from a small place here and a small place here. All right. Now the value f of c is called a local minimum if there exists an interval m and n containing c such that f of x is greater than f of c for all x in that range. So kind of like we were talking about, now we're looking at is the local kind of the minimum. So these were the local max. Now we're looking at local min. And so the value f of c is called a local extremum if either a local maximum or a local minimum is there. Now, a point on a graph where local extremum occurs is also called a turning point. Now, in the figure below, we see the local maximum occurs at C3 and C6. So we're changing directions, and we're changing directions at the maximum, okay? And the local minimum occurs at C2 because now here we're changing directions here, and we're changing directions here at C4. And all four values produce local extrema. Now the points C1 and C5 and C7 way over here are critical numbers, but don't produce local extrema. Okay. Now also the local maximum f of C3, this one right here, is not the largest y coordinate of points on the graph in the figure. So it's not the maximum, there's this value is even higher than this one, but then there's points going on out here too. So we don't know what it's doing out here or down here, but what's given, this is a local maximum, and this is also a local maximum because again, we don't know for sure beyond that. Okay. All right, so here we're supposed to use a graph of G in the figure to find the intervals on which G is decreasing, those on which G is decreasing, any local maxima and any local minima that are involved. All right, so what do we know? Well, this is G of X, so let's start thinking about, okay, well, we can do those. Okay, that's going to be some places where there's going to be local minima and local max. And so we can say the local, if I can find my pen, local minima is going to be where? Well, it's going to be at this point. So it's going to be at 1, 2, 3, x equals -3. And f of -3 is equal to what? Well, that's going to be equal to 1, 2, 3. So it's going to be equal to a -3 also. And over here we have a local maxima, and so that's going to be over 1 up 5. So here we have a local maxima at x equals 1, and f of 1 is equal to a 5. Now, we need to find where it's decreasing, increasing, and over that whole range. So what do we have? Well, it's decreasing here, it's decreasing here, and it's increasing at this point here. Well, although it's going to be kind of shaped the different direction there. It's going to have, can't draw straight here. If that's the inflection point, that's going to be kind of how that would look. All right, so what we have is we have decreasing area and we have an increasing area. Well, is it decreasing? Well, it's decreasing from -infinity up to -3. And it's also decreasing from 1 to +infinity. And it's increasing from -3 to 1. Okay. And so that's all the different pieces that we can get. We can figure out from this graph where it's increasing, where it's decreasing, local max and local min. And again, local max and local min is kind of nice because, we got a horizontal thing here. We can figure that out. But it's also the point where it changes direction. It's going from one point, then it's going back up the direction, going the other direction. So it's decreasing, going to increasing, or increasing, going to decreasing. Oops. All right, so let's stop there and we'll come back for some more.